Okay, I think we are ready to start because afterwards there are still some sessions going on, so I don't want to be late. So it is really a big pleasure for me to be the chair of the talk of Pablo Shmerkin, who actually was an undergraduate student at our university, and he made his undergraduate thesis on fractals, multifractals, with me as an advisor, but I was only there to sign the final work because he did everything by himself. And Pablo has since then worked very prolifically and lately also solving very important conjectures. He is currently at University of British Columbia in Vancouver. He is on leave of the University Torquato di Tella, and we hope that someday he comes back. And well, he won last time the MCA prize. And well, today he's talking to us about counting distances and directions in fractals. All yours, Pablo.
Okay, thank you, Ursula, for the kind introduction. And thank you, everyone, for being here. It's been 2 long weeks, including the sessions last week. And also, there are other nice talks going on at the same time. So thank you for being here. So I'm going to report on a few results that on projects that I've been working on in the last few years. And this includes a collaboration with Tamás Keleti from Eötvös Loránd University in Hungary, Thomas Orpanen from the University of Jyväskylä in Finland, and Wang, who recently started a job at UCLA. Some of this is actually work in progress or very recent. So you will see that some theorems will have a star, meaning that hopefully it will be correct, but it's not fully written down yet. So today I'm going to talk about some problems which are very easy to state, are very difficult to solve. And I think these problems have some sort of a magic appeal to mathematicians. So for example, many problems about the prime numbers or Fermat's last theorem are of this kind. So the problems I'm going to talk about have this flavor. They are not about prime numbers or the integers, but I still think these have this sort of attraction of anybody can understand them, but nobody can solve them. And yeah, so this makes them very interesting. Okay, so we are going to work on RD, where D is at least 2. These problems are not interesting in the real line. They make sense in more general metric spaces, but I'm not going to mention this at all, almost. So in RD, we'll consider the Euclidean distance. And then, so by this, I just mean the Euclidean distance. I hope you can see the cursor, but if not, it doesn't matter. And then if the points are different, I'm also going to consider the direction. So I have 2 points. I look at the direction between the 2 points. It doesn't really matter in anything I'm going to say today, whether the direction is oriented, I go from here to here, as different from going from here to here, or not. It doesn't really matter, take your pick. But according to the formula I'm written here, I'm picking the oriented direction, but this is not really important. Okay, so given any subset of Euclidean space, A, we can consider all the distances spanned by pairs of points in the set. And this I'm going to call the distance set, and I'm going to denote by delta of A, delta distance of A. And then I can also look at all the directions spanned by pairs of distinct points in the set. So I look at all pairs of different points, look at the direction determined by them, and put all of these directions together. And in this way, we get a set theta of A, which I'm going to call the direction set, which is a subset of the circle. So now that the set is in RD, the original set A is in RD, but the distance set is a subset of the non-negative real numbers. So it's a subset of the one-dimensional object, the real line. And the set of directions is a subset of the circle. So it is also a subset of the one-dimensional object. The circle. Sorry. So this is not correct. So first mistake. So I was thinking about the plane here, but okay, no, this doesn't work. Let's try again. Okay, what's going on? This is bad. Okay, so for some reason, this pen isn't working. Maybe I will try to restart this to see if it's fixed. Is that okay? Well, I don't know if it's okay, but I'm going to do it anyway. Okay, still doesn't work. This has never happened to me. I've been teaching using this for months, and this has never happened. So I'm not sure what's going on. Let me try unplugging and plugging the
Well,
tablet.
this is a special seminar. Maybe they have changed some settings. So,
But it should have nothing to do with Zoom. I mean, it should be on my end.
why don't you try with the whiteboard in Zoom?
Oh, it works now. So I reset the tablet and it works now. Yeah, this is not so important. It's just a correction here. So this is actually in the d-1 dimensional sphere. So the distance set is a subset of the real line, but the direction set is a subset of the d-1 sphere. But I wanted to be able to write because I do have to write down things by hand later in the talk. Okay, sorry about this. So the direction set lives in the d-1 sphere. The distance set lives in the real line. And okay, so now I have another problem, but I know how to fix this. Okay, so hopefully everything is fine now. Okay, so a very natural question is, how are the sizes of these objects related? So I have a set A, it has some size, so I'm not telling you what size is. So far this is a heuristic or vague notion, but given a notion of size, what can we say about the size of the distances spanned by points in A, and what can we say about the size of the set of directions spanned by points in A? As I will explain in the next slide, the actually interesting question is, given A, how small can the set of distances and of directions be? Because they can be large. This is not so interesting. The interesting question is, how small can they be? So if we want to make this question precise, the first place to start is by looking at cardinality. So what is the most basic notion of size? Just counting the number of points in the set. So this leads to some very classical and famous problems. So we have a set in Rd, and now it is a finite set. It has n points. And we want to understand what happens asymptotically as n tends to infinity. Maybe we would also be interested in knowing what happens for a specific n, but this is completely hopeless, at least in some cases. So given a set with n points, so given this parameter n, very large, what is the smallest possible number of distances and directions that a set with n points can determine? So this question for distances first appeared in a very famous two-page paper of Erdős in 1946. And since then, it became known as the Erdős distances problem. Erdős didn't actually state any conjecture about this in that paper, but this is also known as Erdős's conjecture on distances. For directions, the problem was raised by Scott in 1970, and actually Scott, when introducing the problem, says that this is an analog to Erdős distance-distances problem. So it was inspired by the distance-distances problem. It's a problem in a very similar spirit. But there is one obvious but important difference, and it is that if all the points are in a line, and I mean, if all the points are in a line, then there is just one direction. So all the pairs of points that are in the same direction. So the problem is not very interesting, but it turns out that it does become interesting if one requires the point not to all be on the same line. And why do we care about finding out what is the smallest number of distances, the smallest number of directions? Because the upper bound is trivial. If we, for example, pick n random points in the unit ball, something like this, we just throw the points at random, then all the distances and all the directions will be different. Other than symmetry, they will all be different. So endpoints certainly can determine roughly n squared distances and n squared directions. And this is in fact the generic situation, in the sense that the random set will have this property. So this problem is not about what happens generically, or these problems. These two problems are not about what happens generically. They are about extremal configurations, special configurations that make the number of distances or directions be smaller than what happens in the generic case. So it turns out that for directions in the plane, this has been completely resolved, completely. So in the plane, Ungar proved in 1982 that endpoints, which are not all on a single line, determine n directions if n is even and n minus 1 if n is odd. And this is completely sharp, and the example showing that it is sharp is a regular polygon with the center. You add the center to the regular polygon. So in the rest of the talk, I'm going to care more about just the order of growth of these numbers and not so much about the precise answer, because usually you cannot get the precise answer. This theorem of Ungar is an exception. So the conceptual point here is that endpoints can determine as few as roughly n directions and no less. And the proof of this theorem is extremely ingenious. So it's a very, very clever argument, but it is elementary. It doesn't really use anything, and it's quite short. It's a couple of pages. Very clever. So if you try to think about this, you're not going to be able to prove it, most likely, because it's very, very clever. But it is self-contained. It's not really connected to any other theory, and it is quite short. But actually, even for this problem, a lot less is known in higher dimensions. So there are some results in R3, but in fact, it's not so clear what are the natural assumptions you need to impose to make this an interesting problem in higher dimensions. Should the points not be coplanar, or what is the right assumption? And with different assumptions, we have different results, but a lot less is known about this in higher dimensions. Okay, so now let's go back to distances. Recall that delta of A is a set of distances spanned by a set A. And in this famous paper in 1946, well, as I said, Erdős actually didn't conjecture anything, but this is known still as Erdős's conjecture. The problem comes from this paper. And the conjecture says that if a set in Rd has n elements, then the set spans at least roughly n to the 2 over d distances. And there is a minus epsilon. I'm going to explain why you don't need the minus epsilon, otherwise it's not true. And I'm going to explain sort of where this conjecture comes from. But the conjecture is endpoints in Rd determine at least roughly n to the 2 to the d distances. So this problem was open in all dimensions for many, many years. There has been progress, so there have been many partial results. There is even a book about partial results, but it was still open until 2010, when Larry Guth and Nets Katz solved the problem in the plane. So they proved this even in a sort of shorter form. So in the plane, of course, d is 2, so 2 over d is 1. So the conjecture in the plane says that a set with n elements determines at least roughly n distances. And Guth and Katz proved this with the log in the denominator, and this log absorbs the n to the minus epsilon terms. So it's even sort of better than n to the minus epsilon. So as I will explain in a couple of minutes, this was a very significant result, both because this problem was very well known and because of the method of proof. But first, let me motivate the conjecture and say something about basically where this numerology comes from. So what is an example of a set with endpoints that determines 3 directions? Okay, so there are some very easy examples one can think of. One is pictured here. It is an arithmetic progression. If you have an arithmetic progression with n elements, then it determines n minus 1 distances, right? So basically what happens here, and the example I'm going to show next, is that each distance that appears in the set is repeated many, many times. So if you want to have few distances, you need to have many repetitions among the distances. So you need the set to be very homogeneous in this sense. And an arithmetic progression has this property. You could also think of a regular polygon. So a regular polygon is very similar, and a regular polygon with n vertices determines roughly n distances. So first of all, what do you do in higher dimensions? And second of all, because in higher dimensions, the set could still be in a line. So it could still be in arithmetic progressions, but then you're not taking advantage of the fact that you have more dimensions to try to do something more clever. And then even in the plane, why do we have this n to the minus epsilon? So in the example of a progression or a polygon, you don't need the n to the minus epsilon. You really have n up to a multiplicative constant. So the example that shows that you don't need the n to the minus epsilon, and the example that in higher dimensions gives you n to the 2 over d is a lattice. And this is sort of a universal example that suggests many conjectures in incidence geometry. So for many conjectures and also theorems in incidence geometry, the extremal configuration is a lattice. So here we have a lattice, which just means points on the integer grid. So we want to have n points in total. So we're going to have square root of n points on each side. And how many distances are determined by this set? Well, we can square the distances. This doesn't change anything. It doesn't change the count of the distances. So if you look at the distances squared, we have the Pythagoras theorem. So the distance squared will be the sum of two integers squared. And these two integers are at most square root of n, right? This is an integer which is at most square root of n. And this is an integer that is at most square root of n. So you have square root of n times square root of n choices for the sides of the triangle. So you have roughly n choices for the distance. So it seems that we are getting n again and nothing better, but in fact we do get something better because the distance squared is again the sum of two integers, the sum of two squares, not just the sum of two integers. It is the sum of two integers, but these integers are squares. And not every integer is the sum of two squares. Most positive integers are not the sum of two squares, and it is a very classical problem in number theory to count how many among the first n integers are sums of two squares. And this is where the n minus epsilon comes from. So the majority of integers are not sum of two squares, although from the point of view of density, most are. Okay, so it's a zero proportion, but it's bigger than n to the minus epsilon for any epsilon. So this is where the n minus epsilon in the conjecture comes from. And in higher dimensions, you take a square root of n times square root, well, not square root of n, sorry. You take a n to the 1 over d times 1 over d times n to the 1 over d lattice. So you do this exactly the same. You want to have n points. So you do this in dimension d. And this is where the n to the 2 over d comes from a lattice in higher dimensions. So people believe that this is sort of the extremal configuration or close to it in the sense that there shouldn't be any sets which considerably fewer distances than the lattice. This is what Erdős's conjecture is saying. So again, Guth and Katz proved this. And this was a really important paper. And so one reason is that, as I said, the problem of Erdős is very easy to state, but very difficult to solve. In fact, Erdős offered $500 as the price for the solution to this problem. And okay, Erdős offered some cash for solutions to many problems, but $500 was a lot. So a $10 problem is already very hard. The $500 is much harder. So I heard a joke once, but at the same time is true, but this is why it's a good joke, that the hardest way to win $1 million is to solve one of the millennium problems in mathematics. Well, I think definitely the hardest way to win $500 is to solve a $500 Erdős problem. So $500 means really hard. And not only that, but Erdős late in his life said that this problem was his main contribution to geometry. And I think this is very interesting because Erdős has over 1,000 papers, and many, or even maybe most of them, deal with geometry in some form. So Erdős proved maybe 1,000 theorems in geometry, but he considered his biggest contribution not any of these theorems, but a conjecture, a problem. So I think this is quite interesting. And as I mentioned several times already, the solution to this conjecture in the plane was a really big breakthrough. And because of this, Guth and Katz received the Clay Award. And Guth, of course, is a great mathematician who did many other amazing things, but this is certainly among the highlights that, well, I guess the organizing committee considered to invite him to next year's ICM as a plenary speaker. Now, another interesting thing from the point of view of the sociology of mathematics, I think, is that, in fact, Guth and Katz used an approach of Elekes and Sharir. So Elekes and Sharir had an idea to approach this problem, but they couldn't actually solve the problem, but they had an idea. And they published this idea. And this is something that doesn't really happen, and it doesn't really happen, okay, for several reasons, but one reason is that very, very few journals would accept such a contribution. So I have an idea to maybe do something. So this is not something that is usually given value. But this development shows that it could potentially have a huge amount of value, because even though Booth and Katz, as I'm going to explain in the next bullet point, they introduced many ideas to this problem. So it's definitely not just some simple observation on top of the framework of Elekes and Sharir. They definitely do rely in a very essential way on the framework of Elekes and Sharir. So it's really a joint contribution. So it's great that Elekes and Sharir, well, unfortunately, Elekes died before seeing the resolution. So Sharir wrote down the ideas, and this was a big part in the solution of the problem. And okay, so there are many important ideas in the solution. It's a highly non-trivial paper, but I guess one I want to highlight, even though I'm not going to go into any details, is a way to partition in Euclidean space using an algebraic variety of defined by a polynomial of small degree, something which is, well, now called polynomial partitioning, or a topological form of the polynomial method. And in fact, this was discussed in some detail in Miguel Walsh's talk, which was a great talk. If you didn't see it, you should go to the YouTube channel of the MCA and watch it, because it's great, and then you can see more about this development. But what is very interesting is that this polynomial partitioning theorem, which again was developed to solve a problem in discrete combinatorial geometry, was later used to make progress on some of the hardest problems in harmonic analysis, which a priori have absolutely nothing to do with the Erdős distances problem. So this shows how a good problem, and Erdős definitely knew this was a good problem, he considered it his main contribution to mathematics, this can lead to developments far away, in far away areas that cannot be anticipated in advance. Of course, you need clever people like Booth and Katz to show the way, but nevertheless, then we can all enjoy this and try to use these techniques that have been developed to do things in our corner of mathematics. Okay, so just one last slide about these discrete problems. So this is absolutely not the end of the story. There are many, many, many variants of this problem that are open. In particular, the problem is still open in dimensions 3 and higher. This problem also makes sense for non-Euclidean norms. And it is conjectured that the fact that the norm is Euclidean is not really important. What is important is the curvature and the smoothness of the unit ball. Then I'm going to talk about this in more detail soon, but there is a very natural pinned version. Pinned means that we fix one point in the set, and then we look at distances from that point to other points in the set. Instead of looking at pairwise distances in general, we fix, we pin, we anchor one of the points and look at distances from that point. And maybe already for one of these pin distance sets, the size is the same as what was conjectured by Erdős, but this does not follow from the Booth and Katz method. Then there is a stronger conjecture in the plane called the unit distance conjecture that says that given a set within elements, the number of pairs such that the distance between the pairs is 1 is at most n to the 1 minus epsilon for any epsilon. And this is actually stronger because basically you are counting how many times each distance can be repeated. So there's nothing special about unit distance. This is for any fixed distance. So if any distance appears at most n times, you need to have at least n distances because you have n squared points. So this is like a much more uniform version, and it's completely open, a very, very hard problem. And as I said before, the belief is that the lattice is an extremal structure for this sort of problems, but nothing is known about this. So there is no theorem, no result at all saying that if there are few distances, the set looks like a lattice in some sense. People believe this, but absolutely nothing is known. So even though there has been very amazing progress, this area is still wide open, and these are really, really hard problems, even though they are very easy to state. Okay, now I'm going to switch to what I do, which is looking at these problems through the lens of geometric measure theory. So instead of measuring the sets using cardinality, I'm going to measure the size of the sets. Okay, I'm not going to look at finite sets. If the sets are finite, we measure using cardinality. But I want to consider compact subsets of Euclidean space. In general, they will be uncountable, so cardinality doesn't work. One could think maybe Lebesgue measure works, but this is not interesting for Lebesgue measure. So a good notion to consider this sort of problems is Hausdorff dimension. So I guess most people in the audience are very familiar with Hausdorff dimension, and we have some experts, but nevertheless, maybe some people aren't, or some people could watch the video later. So let me quickly give you some flavor of what Hausdorff dimension is, because it is really crucial for the rest of the talk. So any subset, absolutely any subset in RD has a Hausdorff dimension, which is a number between 0 and d. And it is a real number. It doesn't have to be an integer. And all the nice properties that you would expect are satisfied. For example, countable sets have 0 dimension. Sets of positive measure have full dimension. A manifold has the same dimension that you already knew it had. So Hausdorff dimension agrees with the smooth notion of dimension. So a k-dimensional variety has dimension k. It is monotone under inclusion, very natural property. It is stable under unions. The dimension of a union is the maximum, or in the case of a countable union, the supremum of the dimensions. And it is invariant under by Lipschitz maps. So these are very reasonable notions of them that a notion of dimension should have. But let me say that these properties do not characterize Hausdorff dimension. There are other notions of dimension that also enjoy this list of properties, which are not Hausdorff dimension. And one of them I'm going to mention very briefly later in the talk. Okay, so very quickly, I'm going to give you the definition. So either you know it, or maybe you're not going to be able to observe it in 1 minute. But so the idea is to define Lebesgue measure, you cover by balls. And the idea is, you know what is the measure of a ball. A ball of radius r has a volume r to the d, up to a constant. And the idea in Hausdorff dimension is you replace d by s, where s is any number, and you find the s that matches the set. So for any set A, there is an S that measure is better than any other possible exponent, and that is the Hausdorff dimension. So this is the idea. So it is an exponent related to efficient coverings of the set by balls. So we are covering the set by balls, and these balls could have possibly different radii, and there is a critical exponent for these coverings, and this is the Hausdorff dimension. So here are some examples. Again, most people are probably familiar with this, but just in case some aren't, this is called a Sierpinski carpet. So it's a nice fractal that has dimension log 8 over log 3. Log 8 because there are 8 pieces, 1, 2, 3, 4, 5, 6, 7, 8. And 3 because each of these 8 pieces is scaled by 1/3. So this is quite close to 2, but not quite. This is a large fractal in the plane. Okay, actually, if you want to study directions or distances in this set, this is not interesting because this Sierpinski carpet contains the boundary of a square. So it contains these 4 segments here. So you will see every direction and every distance. So it's a nice fractal, but not very interesting for the topic of today's talk. So this one is more interesting. It's sort of similar, but thinner. This one has dimension 1. Here the dimension is 1. And this is because you have 3 pieces which are scaled by 1/3. So the dimension is 1. So this is a one-dimensional set that looks nothing like a curve. So a smooth curve has dimension 1, but this is not a smooth curve at all, and it has dimension 1. And this one is a counter set. Topologically, it's a counter set. It's totally disconnected. So in this case, it's not a priori clear what is the set of distances or directions determined by this set. By the way, for this set, we know a lot more because this set is similar. So it has a lot of additional structure compared to an arbitrary compact set. So we actually know more, but it's already non-trivial, quite non-trivial to study directions and distances in a set like this. Okay, and then you can have a fractal like this, which is not so similar like the previous examples. So it doesn't have any obvious recurrent pattern, but still has some dimension. So I don't know what the dimension of this set is. And okay, so this is a set in the plane. Of course, this is an finite approximation. And what can we say about the directions or distances determined by points in this set? So we don't really know. Okay, so now that we know what Hausdorff dimension is, there are some obvious analogs of the questions of Erdős and Scott. We just replace cardinality by dimension. So given a compact set in RD, how are the dimensions? And dimension always means Hausdorff dimension, unless I say otherwise. How are the Hausdorff dimensions of A, the direction set of A, and the distance set of A related? So in particular, given the dimension, a number S, what lower bounds as a function of S can we give for the dimensions of these sets? And as I hinted earlier, it also makes sense and it's natural to look at pinned versions of these problems, where instead of looking at all directions or all distances, we fix one of the 2 points. So we fix a point x, so we pin the directions or the distances at x, and we look at the distances or directions only from that point. And again, it makes sense to ask, what can we say about the dimension of the pinned distance or direction sets? And in the sense that we are trying to find some x which is also in the original set, right? Because if x is in the original set, note that this is a subset of the full distance set. This is a subset of the full direction set if x is in A. And the conjecture is that even fixing the x, we can make it as large as the full set. So it shouldn't, the answer shouldn't really change by pinning the set at some point of x. So I'm not saying every point of x. Here, the order of quantifiers is important. I'm not saying that for every x, this is going to be large. I mean, this is clearly false, right? Because if we have a circle and its center, and we pin at its center, okay, there is only one distance. Let's say a unit circle center at x. If we pin at x, there is only one distance. So we cannot hope to have many distances for every point in the set. But we can hope to have many distances for some point in the set, because in this case, we will pick this point here. And now we have lots of distances, right? Because we can go along the circle. So for people who are not so familiar with fractal geometry or dimensions, let me give a little bit of heuristics of how this problem is related to the discrete problem. And so the bottom line is that they are different, but in some sense, so this is not logically true, but I believe it's fair to say that the version for dimensions are harder. I'm going to explain why. So first, some heuristics. So if in the discrete setting, so there is a cardinality n, there is no cardinality in the continuous world. But if you see an n to the s, okay, you should imagine that this has to do when you go to compact sets to sets of dimension s. So when you want to calculate or estimate or say something about the Hausdorff dimension, something which is quite common, this is not always the case, but something which is quite common is to look at the set at some scale delta. So first you fix delta, you study what happens at scale delta, and then at some later point, you will have to let delta go to 0. But for most of the argument, the scale delta will be fixed. And then you discretize your set. So you're back in some sort of finite situation, but there is a crucial difference. And it is that when you fix your scale delta, what you're doing is, so you have a ball of radius delta, and this means that anything that happens at a smaller resolution becomes just unified. So any points that are a distance less than delta, they become identified. You don't distinguish between them anymore. And this is a crucial difference because, for example, in the Guth and Katz solution of the Erdős problem in the plane, they tell you that there are n distances roughly, but they don't tell you anything about the separation between these distances. So some of these distances could be extremely close to each other, even if the original set is well separated. And then you cannot really get any bound after identifying distances which are under a given scale delta. So this is what, in practice, makes the continuous problems often more difficult. And in most cases, or in many cases, maybe not most, but in many cases, the methods developed in the discrete case do not really adapt to the continuous case. In particular, the polynomial partitioning method of Guth and Katz, even though it's been used for many problems in harmonic analysis, it has not been applied to the distance set problem in the continuous setting, at least not yet. Okay, so with all of this background, this conjecture hopefully is not too surprising. So recall that there is a n to the 2 over d in the Erdős problem, just to give a sense of why this number appears here. So Falconer conjectured in 1985 in the paper where this problem was introduced, that if we have a Borel subset or compact subset of our D, and the dimension is at least half of the dimension of the ambient space, then the distance set spanned by A has Hausdorff dimension 1. And Hausdorff dimension 1 means Hausdorff dimension full, maximal, because the distance set is a subset of the real line. So you cannot have dimension more than 1. So dimension equal to 1 means maximal, many distances. So some comments about this. One is that this d over 2 would be sharp. And again, it would be sharp because of lattices. So you have the example of the lattice, and you can use the lattice as the basis for constructing a Cantor set. So you can do a Cantor type construction where at small scales, the set looks like a very small neighborhood of a lattice. And if you do this carefully, then what you see is that this cannot hold for a number smaller than d over 2. And because this comes from lattices, this is why we believe this is the conjecture. By the way, this conjecture was not explicitly stated as a conjecture in Falconer's paper, but this is the paper where the problem was introduced. Second comment is that I've been talking about compact sets or Borel sets, and there is a very good reason for this, and it is that everything fails if you don't assume any measurability. And in fact, this is more a problem in descriptive set theory if you don't assume measurability, and it was completely solved by Falconer in the original paper. So from now on, even if I don't say that the set is compact or Borel, assume that it is compact or Borel, otherwise everything fails. And unlike the Erdős problem, this is open even in the plane. So it is open in every dimension in which this problem makes sense. It doesn't really make sense in the line. It is open in all dimensions. And in the rest of the talk, I'm going to talk about some partial progress and recent developments, but which are still far from solution in every dimension. Okay, so this is about distances. And of course, again, it makes sense to study the same problem for directions. It's a very similar problem. So in the discrete case, we needed to assume that the set of endpoints to study directions, the set of endpoints is not contained in a line. So when using dimension, there is a very nice way to make absolutely sure that the set is not contained in a line, and that is assuming that the dimension of the set is bigger than 1, because the line has dimension 1. So if the dimension is bigger than 1, it means the set is much bigger than a line. So not only it is not contained in a line, lines are very small compared to the set. So this should help to study directions. And in fact, in the plane, this really does help. And there are many results in this direction, some classical and some new ones. And in fact, if the dimension of a set should be Borel set, it's not written, but always Borel. If the dimension of a Borel set is strictly larger than 1, then in fact, you see pretty much every direction, in the sense that for almost all, okay, there is no measure here. When I say almost all, it means if you put a nice measure on the set for almost all with respect to that measure, or for extremely many. In some sense, don't worry too much about this. For many points in the set, the directions that you see from this fixed point in the set to other points in the set form a set of full Lebesgue measure in the circle. So you see pretty much every direction, at least from a measure theoretical point of view, from most points. So really lots of directions. So these results are quite classical, but in fact, there are more recent developments which turned out to be very, very important. The one comes later. And this is a very vague formulation, but this is a really important theorem of Thomas' opponent, which is quite recent. And basically, the difference is that he considers two sets instead of one set, two sets, and he looks at directions between these two sets. But the key point is that there is a quantitative conclusion that I'm not going to state, but it's not just almost every direction, it is more than this. So he obtains some result on the absolute continuity of some measure, which is a quantitative version that tells you that not only you see many directions, but these directions are very uniformly distributed. And this turns out to be, as I will explain, turns out to be quite important in the study of the Falconer problem. Nevertheless, it also makes sense to ask what happens if the dimension of the set is not at least 1. If it is 1, for example, or possibly less than 1, and then, of course, you need to assume that the set is not contained in a line. And this problem hadn't been studied until quite recently, and Thomas' opponent proved in the same paper, actually. So these are two different results. So this one, okay, this one, and this one. There are two different theorems in the same paper. Okay, and the theorem says that if you have a set of dimension at most 1, which is not contained in a line, which you need to assume, then the set of directions has a dimension at least the dimension of the set over 2. And in fact, even the pink version is true. You can even find an X, so that if you look at directions from that point, you see something of dimension S over 2. And the conjecture, which is a natural conjecture, and was explicitly conjectured also in this paper, is that the real answer is S. So S over 2 is a partial progress, but one really believes that the true answer should be S. Then a couple of years ago, I managed to add an epsilon to this S over 2. So same assumptions, same theorem, it is identical, except that S over 2 becomes S over 2 plus epsilon, where epsilon is a positive number that depends on S. And I'm not sure I'm going to have time, but so there is a large class of problems in this area where adding an epsilon is very difficult, actually. And okay, so I'm relying on other earlier results where you can add an epsilon. So in that sense, maybe this is not so difficult because I'm already using, but don't be, so the message here is, don't assume that adding a very small epsilon is a simple result. Maybe this one is not so difficult, but sometimes adding an epsilon can be very, very hard. Maybe I'm going to spend a minute talking about this a bit later. So this theorem of Orponen is really nice because it's very hard to exploit the fact that A is not contained in a line, because this is a fractal. So even if fractal is not really contained in a line, at a scale delta, it could look like this is contained in a line. For example, it could be contained in a tube of width delta, or it could have very large intersection with the tube of width delta. And this creates all sorts of problems that you do not really have in the discrete setting. So this is another example where the continuous problem is more difficult, so that even showing that this is positive is very hard. In fact, this is the hard part of Orponen's paper. Going from positive to S over 2 is not that hard, but showing that it is positive uses a very clever argument. And actually, my proof of this statement is not just for direction sets. So distances and directions are two concrete examples of a wide variety of problems involving geometric configurations. And the technique used to prove this is actually quite general. And as a final comment, so I don't have anything to announce right now, but I'm working with Wang on two things. First of all, making this epsilon explicit, hopefully. Not just some tiny number, but some explicit number, hopefully not that tiny. And also on higher dimensional versions. So this is in the plane. The higher dimensional problem remains mostly open, and we have some partial results. So in the discrete setting, the direction and distance problems, although they are conceptually related, in fact, they are totally different. They are not connected to each other. And not only that, but the direction problem, even though it's a nice problem, is more like a curiosity. It has a nice solution, it has a full solution, but it's not connected to anything else. While the distance problem was much harder, and because it was much harder, people tried, and in doing so, developed methods and found connections to other areas. So they are really different, and the distance problem turned out to be much deeper. But in the continuous case, it turns out that there is a close connection between these two problems. And this connection goes one way, in the sense that understanding directions better implies understanding distances better. And something very interesting is that this implication that understanding distances better implies understanding directions better, this connection is not a trivial connection, it's not obvious, but it arose in two completely different ways, using two completely different techniques, methods, for totally different reasons. It turned out that you need to understand, or it really helps to understand directions in order to understand distances. So I was hoping to give some intuition of why this is true, but I don't have too much time, so I'm going to skip this, at least for now. If I have some time left, which I probably won't, then I won't come back. Okay, so now is the time to start talking about results. So I've introduced these problems in the continuous setting, but I haven't told you any results. Actually, I have told you about directions, but not about distances. So let me tell you about distances and also more about directions. So we have a problem that we cannot solve. The distance set conjecture we cannot solve. And the distance set conjecture is an implication. If the dimension of the set is d over 2, then the dimension of the distance set is 1. This is the conjecture. So we cannot solve it. So what can we do? So there are three directions we could take in order to make partial progress. One direction is assume more. Instead of assuming that the dimension is d over 2, we assume that it's bigger than some number, concrete number, which is not going to be d over 2. If it's d over 2, you solve the conjecture, but if not, you make it as small as possible, and then conclude what you want. So you assume more and you conclude what you want. And this slide is about this. Other things you can do are assume the original hypothesis that the dimension is d over 2 and see what you can deduce. Even if it's not the full conjecture, maybe you can deduce something interesting. And the third direction is trying to prove the conjecture or something close to it in some special classes, for some special classes of sets. Maybe not for all sets, but for some special classes. So in this slide, I'm focusing on the first line of partial progress, which is assuming more. So instead of assuming that the dimension is d over 2, we are going to assume that the dimension is larger than d over 2, and we're going to prove, in fact, something even stronger. So this means Lebesgue measure. So in this slide, the conclusion is even stronger than dimension 1. The conclusion is positive one-dimensional Lebesgue measure for the distance set. And this is a very fruitful line of research, but this is not where I have worked. This is why there is only one slide, but this is a really important line of research. So already Falconer proved that in RD, if the dimension is at least d over 2 plus 1/2, then the distance set has positive Lebesgue measure. And this has been improved over the years, and there have been contributions for all these people. And if you work in analysis, you know that these are some of the best analysts of the last decades. And also, the list includes some very young analysts that you're going to hear a lot about in the next decades. And okay, so these are the current world records, and these are very deep and difficult results. The current world record is that in even dimension, if a set has dimension bigger than d over 2 plus 1/4, so this a half was reduced to 1/4, then the distance set has positive measure. And in odd dimensions, it's a little bit worse. You have to add something small to this 1/4. Same conclusion. And another progress over this theorem is that even for the pin distance set, we can get the same conclusion. Again, very important, difficult, deep results involving some really, really smart people. Okay, so now finally we can, or I can state some of my contributions. So I don't know how much time I have. Hopefully I have 5 minutes or something like this, but if not, Ursula, feel free to stop me.
You have 10 minutes, Pablo.
10 minutes, okay, fantastic, great, thank you. Okay, so let me finally tell you about some of the things I've been working on. So I have quite a few papers over the last few years. So I'm a slow mathematician, so I'm slowly refining some sort of method adding up new ideas obtained with different collaborators. So this is something I did with Keleti a few years back, and then I refined it a little bit myself. So this is in the plane. In the plane, the assumption is that the dimension of the set is d over 2, which is 1. So we cheat a little bit and assume that the dimension is bigger than 1, just bigger than 1. So it's a little bit of cheating, but not too much. And the result we get is that there are pin distance sets, in particular the full distance set of dimension at least 29 over 42, which is a little bit larger than 2/3. And maybe let's ignore this because there isn't a lot of time. But if you know what packing dimension is, for the packing dimension of the distance set, we get a much better estimate, which in fact is quite close to 1. But this is cheating because the packing dimension is larger than the Hausdorff dimension. If you don't know what packing dimension is, just ignore this comment. So the point is, if the dimension is bigger than 1, then we get an explicit, and I think very reasonable estimate for the dimension of the distance set. No, there is this cheating that the dimension has to be bigger than 1. And this is for the reason I explained earlier, that we need to understand directions to understand distances. And directions are much better understood when the dimension is bigger than 1. So let me advance, and then I'm going to come back to this theorem, and I'm going to put it in context. But let me advance a little bit more. So what if you only assume that the dimension is d over 2? So in the plane, it is equal to 1. Not bigger than 1, but equal to 1. So you don't cheat. Look at the critical case, d over 2. In this case, Falconer proved in 1985 that the dimension of the distance set is at least 1/2. So the conjecture is 1. Falconer proved 1/2. And this is already a non-trivial result. But a much, much deeper result was obtained by putting together a paper of Katz and Tao and a paper of Bulgan. And you can imagine this cannot be easy because 2 of these 3 people are Fields medalists, and Ned Katz is not a Fields medalist, but he could have been. So putting everything together, you see that the only improvement is an epsilon. So this is what I was mentioning earlier. Sometimes adding an epsilon is really, really hard. And in this case, it was really, really hard. And why was it really hard? It is because this is actually false in other settings. For example, in the complex, so you can state a sort of similar conjecture over the complex numbers. And over the complex numbers, you cannot improve 1/2. The answer is 1/2. And the reason for this is that the complex numbers have a half-dimensional ring, which is the real numbers, half the dimension of the complex numbers. Complex numbers dimension 2, the real line half dimension 1. So the real line does not have subrings of dimension 1/2. But in fact, this was an open problem for 14 years. The fact that, so this is a theorem now that was actually proved by Burgan in this paper by adding this epsilon. The real line cannot have Borel subrings of dimension 1/2. If it had, this epsilon would not exist. So this epsilon is actually a big contribution, and this paper of Burgan is extremely, extremely difficult. All of the papers by Burgan are very difficult, but this is just crazy. I don't know if anybody understands it, but thankfully he simplified the proof later and wrote sort of expositions that at least I was able to understand, but not the original paper. So this epsilon was a really big group. Okay, then a couple of years ago, this is related to a result I mentioned about directions. I proved a slightly more sophisticated version of this. First of all, I proved the pinned version. So this method doesn't really apply for pinned versions. And also my method is more flexible. For example, it applies also to other norms. But by the way, I do use this paper of Burgan as a black box, but it's not just that, there is still some work to do. And again, with Wang, we are working on, first of all, making this epsilon explicit and hopefully not too small, and also getting versions of this in higher dimensions, and in particular in R3. So this is a theorem with a star because it's not fully written down, but we hope to be able to show that if we have a compact set of dimension 3/2 in R3, so this is a critical value, then there are points in A so that the pin distance set has dimension at least 1/2, but for Falconer, plus 1/70. So epsilon is 1/70, which might seem to you a bit small, but actually it is huge compared with the epsilon in Burgan's work. In Burgan's work, the epsilon is not explicit, but it's really, really, really small. So many, many, many orders of magnitude smaller than 1/70. So I want to emphasize that this is not just looking at this proof and making it quantitative. It is not. If you do that, you will end up with 10 to the minus 100 instead of 1/70 or something like that. Okay, so finally, so a last direction in which one can hope to make progress is by considering some special examples or classes of examples. And in geometric measure theory, a very natural class of examples are Alfred's regular sets. So Alfred's regular sets with parameter s, with exponent s, have dimension s, but in a very uniform way. If you're not familiar with the concept, this is what you should think about. So all over the place, wherever you look and whatever scale you look, you see an s-dimensional set. So this is the idea of an Alfred's regular set. And this is a very, very well-known, a very important class. And in fact, I'm going to state some results for Alfred's regular sets. And let me just very briefly mention that, in fact, they hold for a much wider class of sets, not just Alfred's regular. But Alfred's regular are easy to define and well-known. So I'm going to just state the results for Alfred's regular sets. And the short version is that we know a lot more for Alfred's regular sets. And hopefully, so this is not written down and I don't want to claim it, but hopefully we even know the full conjecture for Alfred's regular sets. So I think this could be in reach, although not done as of today. So a few years ago, I proved that under this cheating, so we have the cheating again. First of all, we are in the plane. It's not written here, but in the plane, under this cheating that the dimension is not 1, but bigger than 1, I proved the actual conjecture. So the distance set has dimension 1 for Alfred's regular sets. Again, this S larger than 1 was really important because I relied on results about directions, which are much better understood when the dimension is bigger than 1. But now, hopefully, I can also do it for dimension 1. And this is a consequence, not a completely immediate consequence, but it relies very, very strongly on a recent joint work with Thomas Orponen, which in turn relies on an older work of Thomas Orponen on a different problem called the Furstenberg set problem. So everything is connected. And this is what I hope to explain in the last couple of minutes. So this is for directions. And for directions, hopefully I'm able to prove the conjecture for Alfred's regular sets in the plane. So this is not written here, but in the plane. So if they are not contained in a line, then the set of directions, the set determines, is 1, which is the largest possible. And because understanding directions implies understanding distances, then hopefully, so there is a star, But hopefully, the same is true for distance sets. So if this turns out to be correct, which I hope it is, this is the full solution to the conjecture for alpha regular sets in the plane, because now they are really one-dimensional, not bigger than one, but equal to one. And again, the conclusion is the conclusion of the conjecture. Dimension is one, even the stronger form where you pin the distances at a given point x. So let me finish. Hopefully, I have 2 minutes. Let me finish on a more philosophical, well, sort of a broad discussion, but a little bit philosophical, about how these problems that were stated because they were interesting in themselves turned out to be connected to so many other things. So the line of progress in which, assuming a larger bound on the dimension, you show that, not you, but these various people show that the distance has positive measure. All of this is done using restriction theory. And restriction theory is a key area of harmonic analysis. And the connection between the distance set problem or conjecture and restriction theory was done by Tella very soon after Falconer came out with his paper. And this connection continues to be developed. So whenever there are advances in restriction theory, they lead to advances in the Falconer distance set problem. And this is at the heart of some of the very recent developments. Another sort of field that doesn't seem to have a lot to do, but turns out to have a lot to do with the distance set problem is additive combinatorics. So one crucial problem in additive combinatorics is, given a subset of the reals, one believes that either the sum set or the product set should be much larger than A, in fact, as large as possible in some sense. So this is a general principle that, again, should hold for different notions of size, and there is a fractal version of that. And this fractal version was connected to the distance set problem by Katz and Tao, and this is closely related to this epsilon gain that Bourgain later proved, as I explained earlier. So Katz, Tao, Bourgain found the connection with a very active and important area called additive combinatorics, which apparently has nothing to do with the problem. This is maybe less surprising, but there are lots of connections with geometric measure theory. This is a problem in geometric measure theory, so I guess it's not surprising that there are connections. But the kind of connections that have been developed were not at all obvious in principle. And what I think is interesting is that the distance set problem has stimulated new results in geometric measure theory that a priori have not much to do with it. And there are also some combinatorial problems involving Lipschitz functions that, again, seem to have nothing to do with the problem, but that are quite important in the method that I developed together with Tamás Keleti and later. Okay, so the conclusion is that in mathematics, it often happens that you think of a problem because it's a natural problem, you have curiosity, not because it is connected to some big theory, but nevertheless, trying to solve the problems, the community finds many deep connections, and in the end, other fields, maybe fields which are connected to big theories, end up advancing because people try to solve these concrete problems first. Okay, thank you very much.
Thank you very much, Pablo. You managed to finish on time, so thank you for that also. Are there any questions? Feel free to unmute yourself and ask if you have any question. There is nothing in the chat, so if somebody would like to ask something, feel free.
I have a question.
Pablo.
May I? Well, first of all, thanks, Pablo, for this beautiful talk, really amazing.
Thank you.
At least the small part that I've been able to understand. I would like to say something just to check if I'm completely wrong or it makes some sense. I mean, this distance is set and direction set. Is it at least in somehow correct to say that has to do with the complexity of the set, or is any weight or has nothing to do with that?
Well, how do you define or what do you mean by complexity?
Exactly.
So,
I mean, this could be some kind of definition of complexity or.
Well, I mean, again, so what people believe is that sets that look like lattices, that have big intersection with the lattice, things like this, should be the sets that have few distances and few directions. And a lattice, of course, has a lot of structure, but this is a very heuristic viewpoint. So there are no results at all in this direction. So I think people believe that if a set has few distances, if a set has few directions, then it should have maybe low complexity or high complexity, maybe depends. So there could be a connection, but I think this is completely beyond the reach of what can be proved currently.
And the other question related to that is that, okay, so there is this direction set, which is d-1 dimensional, and then the distance set, which is 1 dimensional. So is there anything in between them, or that makes sense to consider like sets of?
Yes, I mean, well, I don't know if in the middle, but I mean, certainly there are many variants that have been studied. For example, so you can look at, instead of 2 points, you can pick 3 points, and you can look at the sort of triangles. So you can look at the side of the triangles, or you can look at the area of the triangle. So instead of 2 points, you can pick any number of points, and then look at geometric configurations spanned by these points. You have an infinite variety of problems, and all of these problems have been studied. And
okay,
so sort of the phase space where the space of configuration lives, which is 1 dimensional for distances and d-1 dimensional for directions, you can get really any dimension. So it depends on what geometric configuration you look at.
And all of them has to do with this some kind of notion of complexity, right? Like in some way they are encoding the complexity of the set, right?
Well, so again, so it depends how you define complexity.
Yeah.
But
I mean,
so all of these results are about relating the size of the set to the size of the distances. But it would be interesting to understand how the structure of the set relates to the distances or directions or other configurations. But again, this is much harder. So already for size, it's very, very hard. If you want to get some finer information, it's hopeless at the moment.
thanks.
Mm-hmm.
Any further questions?
I have another one if there is time.
Mm-hmm.
So about I guess this is more related to the discrete setting. So you fix d and you take n to infinity. And my question if it makes sense and there is something to say when if you fix n and you take d to infinity. Like,
sorry, you take what?
The dimension of the space.
The dimension to infinity. Like you consider n points and then you fix the n points and then you take the dimension like very, very large.
Okay, but in that case, this is not interesting because if you have a lattice with n points in dimension d, you can have n to the 2 over d distances. And as d tends to infinity, this tends to 1. So the answer is 1.
That's it.
Yeah.
Yeah.
For other problems, this might make sense, but for distances at least, the lattice shows that you get fewer. So if you fix the number of points, being in a larger dimension really allows you to have fewer distances.
Yeah. Well, so if there are no further questions, let us thank Pablo again.
Okay.